Okay, so I'm going to just bring up a few minor comments about Chapter 2. So first of all, let's talk about control structures. So what I mean by control structures is the way that Maple lets you design your program, in the sense that there's various commands in your program, usually of some sort of mathematical nature. Something is computed or stored somewhere or retrieved from somewhere, and the control structure makes sure that things are done in the right order, in the order that you wish. And Maple is a very sort of classical programming language in this sense. It has various ways of making repetition, and it has various ways of making choices. And so, I mean, what I mean by repetition, and I'm just drawing a suggestive figure in the sort of old-fashioned way of a flow chart. So the way this works is that you start out by asking some sort of question. So you are interested in some sort of condition being true or false. And if the condition is true, so then you move on down to the next statement, and you do this for a while. And then you go up again and see if the statement remains true, and so on. Right? And then at the end of the procedure, if this is no longer true, then it becomes false, and you break out of this repetition. So this is done in Maple in various ways. We will discuss them next week. There's a for loop. A for loop is a very sort of controlled way of making repetition, where you know from the beginning that you want to do something, say 10 times. Then you will say for I from 1 to 10 do, and then the conditions that you want to have repeated 10 times. And then at the end, you put in some end command. Right? So, I mean, essentially, there will be for, and then it will check that the counter that we're looking at is still not at the end of the number of ways we want to do this. So there's something that I'm not writing here. Then we say do, and then down here we say end or end do, and then in between here we have the commands that we want to repeat. So and then when the program is finished, in the sense that we've done this the number of times that we were intending to, then we go on here in the next line. There's also something called a while command that is a little bit more versatile, so it will check not just a counter that is updated automatically, it can check more complicated statements, but it has the same sort of syntax: while certain statement is true, do, and then you repeat these things until an end do. And by the way, these do's here are optional, so you can just write end. Of course, it's quicker to write end. The advantage of writing end do is that this is like a parenthesis that then Maple can check that it's matched with the correct kind of beginning. It's like a closing parenthesis, so Maple can check that it's matched with the correct kind of opening parenthesis. And then, of course, as you can read in the book, there's all kinds of things that can go wrong. In particular, if you have a while setting, then maybe if you're not careful, it's impossible for your program to make the statement false, and then you'll be running in an infinite loop. This will not happen as easily with a for loop, but actually you can also, as we give examples of, you can actually also put yourself in this kind of situation. So, of course, an infinite loop is a priori it's a bad thing, because it means that your program never finishes, but actually in some situations we're just going to work with infinite loops, in the sense that we want to get as much information out as we can, and then we will just, instead of trying to figure out how much information we are able to get out in the time that we have. We will just sort of keep running until we lose patience and shut down Maple. I mean, so that's the idea behind the sort of controlled infinite loops that we will do. So this is one kind of control structure, and a second kind of control structure is the if statement. So that has a similar nature. So it works like this in its most basic form. So I ask a certain question, and if the answer is yes, I evaluate this thing down here, and if the answer is no, I don't evaluate this thing down here. And this will be if, then you have the statement, you say ... then, and then you have some statements here, and then there's an end if at the end. So this, again, this is a conditional statement. You will only do this in case something is true. So in the example that we just looked at the exercises, I had an if statement saying that if we had that these numbers were mutually prime, then I would print something out, and if they weren't, I would not print something out. This is a very basic kind of if statement. And actually there's variations where you can have more systematically a situation like this. So you have your question, and then if it's true, you want to do this, and if it's false, you want to do that, and then resume at the next line. So that's if, then, and then there's else, and if. So here you put the thing you want to happen if the statement is if the statement is true, and here you put what you want to happen if the statement is false. And there's even a way of getting more than two choices using an elif command, which I don't think I want to explain for now. So what I hope you will pay attention to in chapter 2 in particular are these beginning discussions of what is a good way of organizing code in Maple for a mathematical experiment. And so we have the concept that I've already introduced you to of pseudocode. There's also the concept of stepwise refinement. And there's the concept, or maybe just the idea of small units. So, I mean, this is sort of three things that work in the same direction. So pseudocode is the idea that when you design your experiment or the code that you wish to execute in order to conduct the experiment, you don't sit down and program directly. First you design it in a more general way, where you sort of say, instead of writing Maple code, you write in sort of a hybrid between Maple code or programming language and human language, something which is perhaps could be as superficial as saying until we have a counterexample, compute the next one and print what happens, or something like that. And then the idea of stepwise refinement is that as soon as you have this very coarse description of your program, you will take the various lines of your pseudocode and expand those into more detailed code. This has the advantage that it will help you produce small units. What I mean by small units is that suppose that you see in your program that the same thing needs to be done more than one place, then you can break that out into a procedure, because you have now seen that this procedure is something that you need to do at 2 or 3 or more places in your code. So you can say, okay, this is a common thing that needs to be repeated, so I will do this once and for all. Right, so if you make your program this way, it's a very good idea to always try to reuse your code as much as possible. I would say for two different reasons, right? One is, of course, it's a good idea to reuse code because it's efficient. So if you've written a program that does something, you might as well use it in any possible context. But really what is perhaps more important is that you also only need to debug it once, right? So that if you know that this works, you can use it freely all over your code. But another very important advantage of this way of writing your program is that it also becomes much easier to read. Because if you have sort of analyzed your program into small procedures that talk together in possibly very intricate ways, it's going to be much easier to read and understand and change, if that's necessary, if indeed you have the setup that I described. Whereas if you write a long program that does everything in a sort of a long string of commands put after each other, then most experience will say that you will have things that are much less easy to understand. So I think, explaining pseudocode and stepwise refinement isn't so easy because it's sort of an idea rather than a precise method. But I think it will be fairly clear when you do exercises and when you do the assignments how that's going to play out. And in particular, when we reach the end of the course and you need to do your big assignment, if you have organized things in an efficient way, it's going to be much easier for us to read it and to perhaps tweak it and change it into things that are slightly more useful than what you did. Whereas if you write a long sort of spaghetti code type of program, it's going to be very difficult for us to follow what you do. This, of course, is also I don't want to sound too religious here, because of course we all know that when we're engaged in trying to do something interesting like a mathematical experiment, it's very easy to get carried away and to sort of change things and move things around and make long, maybe clumsy solutions to the problems that we have. So that's a very human thing. I do it myself, so I'm not trying to be very this is not a moral thing, but it's a practical thing. It's really a very good thing if you can do things systematically, if you can keep track of the various versions of Maple that you did. Don't overwrite everything that you did. If you did an experiment on Tuesday, save it as experiment Tuesday so that you can find it again and then keep working on it, and then you do an experiment Wednesday, you save that, maybe even more in the same day, of course. And also do some sort of a log, like you were if you were to do a real experiment in chemistry or physics or so. There's a physical book that people write down what they did, mainly because it's not always sound to have computers in a lab, but you can keep track of what you did because you might need it again. That's a very important part of when you program. Try to be as systematic as possible and try to save things so that you can return to them later. Okay, so this is one part of good programming practice that I want to emphasize. Then there's the idea of need to know, and maybe I should write no magic numbers. So the need to know principle is that whenever you write a part of your program, think about what this part of the program needs to know in order to do its job, and give it that information and nothing more. So this is very easily seen. If you make your program without global variables, then you'll have a procedure that takes some input, and that input needs to be precisely what is needed in order to produce the output. Right? So if you give something to your procedure that's not used to produce the output, then remove it from the input. Even though, I mean, that's not really going to change anything. Maple doesn't really care if you give it some information that it doesn't need to use. That's not going to slow it down or anything, but it's going to be much easier to understand what the program does and also to debug it if it has the information that it needs to do its job and nothing else. So that's the idea of a need to know. The idea of magic numbers is that when you sit down and do an experiment, you might decide in the beginning that you want to compute all the numbers until 20. And then you sit and you write your code, and then you write 20 whenever you have to decide on the size of a for loop or whatever. But then it will happen, I can assure you, that at some point you will think, oh, it would be nice if I could do this to 50, not just 20. So that's when you fall into the trap of using a magic number. 20 becomes a magic number that you repeat in your program, and then when you decide you want to change that, you have to sort of search and replace. And if you're unlucky, then maybe somewhere you need to do 2 times 20, and then you've written 40 instead, and so on. So what is a really good idea to do this here is that at the very beginning of your program, you write n equals 20, and then you write n instead of 20 when you make your program. Now, if you decide that 20 was not enough, it's very easy to go back, change 20 to 50, and then run the whole program again, and hopefully that should work. So that's also a very basic thing, but this is, we all fall into this trap, and it's good to be prepared. The final thing, and so these are also sort of related issues. The final thing I would like to emphasize is the idea of efficiency later. So what I mean by efficiency later is when you design your program, of course, most of the time you should be prepared to think about efficiency of your program. Because unless you're really lucky with your experiment, you will have to put some CPU power into this question. And if you've written an inefficient program, this may take, to reach the amount of data that you need. If you've written an inefficient program, this will take 24 hours, and if you've written an efficient program, it will take half an hour. And of course, there's a huge difference between assigning your computer to doing something for 24 hours as compared to half an hour. So efficiency is definitely important. But I think for doing mathematical experiments, and also for writing programs, if you're not super experienced, it's a good idea to postpone the discussion of efficiency. So I think for here it's a good principle to just say, let's not care about efficiency the first iteration of the program we write. Perhaps we're lucky and the inefficient program or the naive program that we wrote will be good enough for what we want to do. That's a possibility. And even if we're not that lucky, we need to write a more efficient program. It's very nice to have an inefficient program that we know works to test the efficient program. So I will generally recommend that you don't think so much about efficiency when you start your experiments, and then if at the end of the day you see that you have to be more clever in your program, you have to return to it. And also at the very end of the course we have a week about how you do this in Maple. So of course, I mean, depends on the context how relaxed you can afford to be about efficiency, but as a general principle, let's not worry about it from the outset of the experiments. Okay, so that's what I wanted to say about chapter 2. Then I'll make a final screencast about the example about Chebyshev bias in a second.